Hi everyone, I am Jiacheng Wang from Zhejiang University. I am going to introduce Tac-Trainer, the visual analytics system for IoT-based racket sport training. Conventional knowledge-driven training method relies on coach's knowledge and experience, which can be biased in some conditions. To remove the biases, IoT-based data-driven methods are proposed. However, these methods are not friendly for coaches. Therefore, we integrate these two types of methods and propose an IoT plus visual analytics framework, Tac-Trainer. Currently, IoT technology has been widely studied in sports training. Various devices have been introduced to collect trainees' detailed kinematic data during the training. Researchers use the data to investigate tasks such as action recognition and skill assessment. However, these studies cannot provide actionable insights for coaches. Besides, some commercial products are also released for users to collect and analyze the training process. However, these products only present basic statistical results. The fine-grained training data is not available for customized analysis. To facilitate the analysis of the motion data collected by sensors, researchers developed various visual analytics systems. These systems are used to analyze characteristics of motions of the upper extremity, brachial plexus injuries, and even the motions of horses. However, systems for visual analytics of the motion data in sports training are rarely studied. In the field of sports data visualization, considerable visual analytics systems are developed for the analysis of various sports, such as soccer, basketball, tennis, and table tennis. While these systems can help discover variable insights, they focus on the data of formal matches instead of the training process. Due to the difference of the data type and analysis goals, these systems cannot be extended to our scenario. Besides, several virtual reality systems are also developed for the training of table tennis. However, we want to solve problems in the real-world environment instead of the virtual environment. Therefore, we propose Tac-Trainer. To construct Tac-Trainer, we faced two challenges. The first is how to coordinate the sensor data and the information extracted by models for coaches. And the second is how to provide effective and efficient analysis for coaches. To solve the first challenge, we collaborate with three experts and summarize their requirements and considerations when analyzing the data collected by the IoT devices. With these considerations, we developed an IoT plus VA framework, Tac-Trainer, which solved the second challenge. The framework consists of four components: device configuration, data interpretation, training optimization, and result visualization. Device configuration configures IoT devices for data collection. Data interpretation detects valid actions from the sensor data first. Then, it recognizes the technical attributes and estimates the performance indicators of the actions. Training optimization helps coaches assess the actions based on the results of data interpretation and generates optimization strategies for the poorly performed actions. Result visualization visualizes the process and the results of data interpretation and training optimization for coaches to analyze. In device configuration, we used four devices fixed on the racket, the right wrist, the right arm, and the left wrist, respectively. Each device contains a 9-axis gyroscope. The parameters of the devices are presented in the table below. Data interpretation is responsible for attribute recognition and indicator estimation. Before these two tasks, we need to detect and extract the sensor data of the stroke. We used the acceleration signals to detect strokes, since explicit peaks exist in all axes of these signals. We computed the energy of all signals and used conventional peak detection algorithms to detect the strokes. Then we trained two classifiers to recognize the technique and the position of each stroke based on the center data of each stroke. We tried many classifiers and the random forest performed the best among them. Finally, we used two regression models to estimate the speed and spin of each stroke. We also tried many models and similarly, random forest outperformed others. Therefore, we choose random forest for attribute recognition and indicator estimation. To be mentioned, to annotate the training data of speed and spin estimation, we drew special icons on the table tennis balls. We used a high-speed camera to capture the ball served by the ball machine. In such a manner, we annotated the specific values of the ball spin and speed. In training optimization, we first provide interactive methods to help coaches find the poorly performed strokes. We will introduce the interactions later. Then we generate the optimized suggestions for the poorly performed strokes. Here, we reconstructed trainees' movement trajectories. For example, the red line here presents the trajectory of the trainee's racket when hitting the poorly performed stroke. The blue line presents the optimized trajectory of the trainee's racket, which means if the trainee swings the racket in such a trajectory, he or she can improve the performance of this stroke. In such a way, we provide suggestions for trainees. In result visualization, we developed a visual analytics system to visualize all processes and results. The system contains two views, the training view and the suggestion view. In the training view, each flow presents the complete training. We used the glyph to encode the stroke in the training. We used the metaphor of the dashboard to encode the speed and spin of the stroke. Besides, we referred previous work and encode the technique and position on the glyph. In the suggestion view, coaches can explore the trajectories of each optimization suggestion in 3D plots. Before analysis, coaches can use the system to record and visualize new training data. They need to first bind the sensors with trainees' joints first. Then the system will record and visualize trainees' data in real time. Here, after the trainee hit the stroke, the glyph would exist in the training flow. After finishing the training, coaches can explore each stroke and move the slider to assess and find the bad strokes in the training view. Coaches can choose the bad stroke and click the optimization button in the suggestion view. In the suggestion list, coaches can choose the suggestion of interest to explore in the 3D view. That's all. Thank you.